This is a brief video presentation of dcbench, a benchmark for data-centric AI systems. It targets system components that were designed for solving pain points that creep up along the data-centric AI development workflow. In recent years, the machine learning systems and data management communities have been working hard to solve many of these pain points. However, we believe that there are still a lot of pain points that are left unsolved, and a lot of potential for even more impactful future work. Our motivation for building dcbench was to make it easy both to evaluate those existing solutions, but also to motivate future work in this exciting space. Let's first try to get the obvious question out of the way. Why do we need another ML benchmark? If we take a look at the space of existing benchmarks, we might notice that they fall into two groups. The first group we can call quality benchmarks, such as ImageNet, that evaluate the quality of a model on some specific ML task. The second are efficiency benchmarks, such as MLPerf, that measure the speed of model training and inference achieved with some specific hardware or software platforms. However, if we take a look at the workflow of modern-day ML development, we will notice a much broader picture. The data used to train the ML model is not a static entity. It is derived from our raw input data by passing it through a complex ML development process. Similarly, before a trained ML model reaches the development stage, it is passed through a similarly complex operational cycle guided by the help of fresh production data. Due to their complexity and lack of clear guidance, these processes are often overwhelming for ML developers. Therefore, navigating and managing these processes is an emerging and active area of ML systems research. There is a great amount of next-generation ML system components that are just waiting to be built. Each one can solve some real pain point that ML developers experience. With that in mind, we built dcbench, a benchmark for evaluating the next generation of ML system components. We provide a growing list of benchmark tasks, each one focused around some future ML system component. We can view this hypothetical system component as a program that takes some input artifacts and produces output artifacts. As a benchmark participant, your first step would be to design and implement a system component that can solve the pain point that the benchmark task of your choice is built around. A benchmark task contains a collection of problems, each one characterized with some set of attributes that let us group problems in various interesting ways. Each problem comes with a set of problem artifacts, some of which are used as input artifacts and others are used for evaluation. Your job would be to produce solution artifacts by using the system component you built. The task documentation contains a description of provided problem artifacts and expected solution artifacts. Using all these artifacts, we can perform an evaluation and produce an evaluation result. By repeating this process for all problems, we end up with a collection of evaluation results which together constitute a benchmark measurement. We can aggregate this measurement, potentially grouped by various problem attributes, and produce benchmark scoreboards. These scoreboards allow us to gain various insights about the quality of your system component, as well as allowing us to compare the quality of different components. We're now going to show you a brief demonstration of dcbench and walk you through one specific task, slice discovery.
We'll begin by pip installing dcbench. Usually this is the only step needed to get started, but for special cases, more detailed instructions can be found in our documentation. Next, we'll import dcbench and list available tasks. We can get more details on these tasks in the documentation. dcbench is designed to support a diverse set of data-centric tasks from across the machine learning lifecycle. For example, in data cleaning on a budget, we provide a benchmark for evaluating techniques that identify data points to clean. In this video, we'll focus on a different task called slice discovery. Before we dive in, let's provide some quick background on this pretty interesting task. Machine learning models that achieve high overall accuracy often make systematic errors on coherent slices of validation data. As an example, a model trained to detect birds may perform poorly in front of trees. If the trees are annotated in our dataset, then we can split the dataset into groups and identify this problem. The trouble is, in practice, many data slices are hidden, meaning they are not annotated in the metadata. Slice discovery is the task of mining unstructured input data for important slices on which a model performs poorly. We start with a labeled dataset and a train classifier, which are fed as inputs to a slice discovery method. This is an algorithm that splits the dataset into slices based on the model's errors. To evaluate the slice discovery method, we compare the discovered slices to ground truth slices on which we know the model performs poorly. In dcbench, we package an instantiation of this task as a problem. A problem consists of a dataset and a classifier, the inputs, and ground truth slices, the outputs. dcbench provides nearly 1,000 slice discovery problems, which enable systematic evaluations of slice discovery methods. We can list these problems in a notebook using the Python API. Each row in the table corresponds to one problem and is uniquely identified by a problem ID on the left. Let's look at one of these problems in a bit more detail. Each problem is associated with a set of attributes. For example, the dataset attribute tells us what dataset this problem is derived from. The target name attribute tells us that the model was trained to predict cats, and the slice name attribute tells us that the model underperforms on a specific type of cat, cougar. Recall that a slice discovery problem includes inputs, a model and dataset, and outputs, the ground truth slices. In dcbench, inputs and outputs are provided as problem artifacts. Each artifact is kept in dcbench cloud storage. For example, in this problem, the weights and configuration of the model are provided through an artifact called model, and using the API, we can access the artifact's URL. But in practice, we don't need to worry about downloading artifacts or interacting with URLs. We can load the artifact into memory with a single line of code using bracket notation. Behind the scenes, dcbench handles the downloading and caching of data. The second slice discovery input is the dataset. This input is actually split between multiple artifacts. We'll construct a table representing the dataset by joining two tables, one containing validation predictions and another containing the images. Notice that the resulting table has columns for the images, binary labels for the cats, and the model's predictions. One of our goals with dcbench was to reduce the time required to start experimenting with new methods. To demonstrate, we'll dive right in and apply a slice discovery method to the problem we've just loaded. We'll be using Domino, a Python package providing implementations of common slice discovery methods. We first embed the images in the dataset using an image encoder. Here, we use clip, a cross-modal encoder. Next, we fit a mixture model to identify regions in the embedding space where the model performs poorly. We'll apply the mixture model to the test set, which yields our discovered slices. Returning to the dcbench API, we can create a solution which contains these discovered slices. Central to dcbench are the evaluation metrics used to measure the quality of a solution. Computing metrics with the evaluate method, we see that our method has roughly identified the hidden ground truth slice, posting an average precision above 0.8. We can also inspect the discovered slices ourselves, and sure enough, one of them is composed primarily of cougars. With dcbench, we wanted to make it easy to transition from experimentation on one or two problems to large-scale evaluation across many problems. Because all problems in dcbench have the same format, we can pass the same algorithm we used above to an evaluation script, which will run the method on all of the problems in the task. We have nearly 1,000 slice discovery problems, so running these large-scale evaluations can be expensive. But with the numworkers argument, we can instruct dcbench to parallelize things using array. This packages the solution into a solution set, which is saved to disk with a unique ID and can be loaded later. To analyze performance, we can ask dcbench for a data frame with metrics across all 886 problems. Using the problem attributes we discussed earlier, we can stratify and perform fine-grained analyses that show what kinds of problems our method performs well on, highlighting its strengths and weaknesses. We'll stop there for this video, but if you're interested in learning more, please check out our documentation or reach out on GitHub.